Okay, right. Basically, we are in the middle of chapter 4. Hopefully, we can finish like the third quarter of this chapter, or probably if we can finish like within today or so, it would be good. So, I think we are until here, until polarization, concentration polarization. But before that, probably we can like recap what we have learned last week, especially on polarization. I've seen your homework on the Butler-Volmer equation. I think most of you did very well. And do you guys have any problem? Anything that you want to ask before we continue? Okay, so basically for activation polarization, we have, studied what is meant by anodic polarization, what is meant by cathodic polarization. In a normal condition, where the anodic and cathodic, or the forward and reverse reaction is equal, we are going to assume as the process like this. You are going to produce like a similar exchange current density for forward and also reverse reaction. And basically what happened is that when you actually increase the potential, okay, from the equilibrium potential, bigger or lower, then this phenomena is called as polarization. And the values of a positive shift or negatively shift of potential is known as overpotential. So we have looked through the anodic current density when you experience anodic polarization, and also cathodic current density when you experience uh, reverse reaction, okay, or cathodic polarization. So this is basically what you have seen. As I said, this part is quite important for you guys to understand or to memorize. At least if you cannot really understand, you just need to memorize, because I think in this chapter, the essential part will be on the derivation of anodic current density, cathodic current density, Butler-Volmer equation, and also Teffel's slope. So only this equation that you guys need to memorize, because I think in exam and also in a test, normally I will ask this kind of question, either one of these equation to be asked during exam. So please put in your mind, at least you can memorize the steps and others. Okay, right. So we also have looked at Butler-Volmer equation, how we can get Butler-Volmer equation. It's actually the combination of anodic current density and also cathodic current density. And we have also looked at the plot that you will get when you do polarization techniques. Of course, you will get this curve. It's known as a linear polarization curve. It's basically potential versus current, or current versus potential plot. And apart from a linear plot, you can also make the current density into log, where you will get the so-called Teffer plot. So I think for the Teffer plot, we are going to like study more details in chapter 5, I think the last chapter, in potential dynamic polarization methods. And for Teffer slope also, we have looked through how we are going to like derive this equation. So what does it mean by Teffer slope? Teffer slope is basically the beta anodic and beta cathodic. Beta anodic and beta cathodic, you can get it from Teffer plot. It's actually the slope of anodic and also the slope of cathodic. All right. And today we are going to continue with concentration polarization. Okay. So for concentration polarization, one of the assumptions in derivation of Butler-Volmer equation is the uniformity of concentration near the electrode. This assumption fails at higher current density because migration of ion towards the electrode from bulk is slow and may become rate determining. a larger overpotential is then needed to produce a given current because the supply of reducible or oxidizable species have been depleted. This effect is known as concentration polarization. Okay, so for concentration polarization, this actually consider the effect of, as I said before, the concentration effect. That is why the name itself indicates the phenomenon. So if you actually still remember about double layer, we have electrodes. And when the electrode is basically oxidized, okay, the first process that happens is actually migration. Okay, you have the electrostatic interaction between the negatively charged species on the surface of electrode at inner Helmholtz plane. Okay, and then at the outer Helmholtz plane, okay, OHP, this is where you have the remaining concentration. Right. So here in this region, you will notice that the concentration of anion will always going to be higher. Okay. So this actually can disturb the polarization method. Process, because some of the current that been supplied from oxidation or reduction have been depleted. Depleted means that it is not negligible, it's too small or what. Okay, because this effect is more major. Okay, so this actually known as concentration polarization. All right. So for any potential that deals with the effect of activity or concentration, then you will have a representation. In fact, in Nernst equation, concentration will give some effect to the potential values. So that is why I think P. EP is basically a polarization potential. Okay. And then polarization potential is basically equals to standard potential plus with RT over NF ln CS. So CS is basically the concentration of the solutes. Okay. All right. So the concentration of solutes and also the concentration of the bulk. So this basically what it is mentioning on. So in fact, when you look at this potential diagram, so you will see that it's almost the same as what we have explained earlier for the Helmholtz. It has a linear drop of potential values from like zero until from zero current. So you will see that there's a linear trend that indicates that the process is basically experience Helmholtz double layer or migration, which actually giving a rise to concentration effects. All right. When we talk about concentration difference and related after that will be on diffusion. So we also need to understand that diffusion also occurs by the the movement or the creation of flux. So this is not something that you have to remember or what. It is just to, explain the concept of diffusion of flux. Okay. So you can see that over here from Fick's first law, this is actually the diffusion law proposed by Fick's. You'll have like J is basically the current density. Current density is actually equals to the minus diffusivity multiply with the difference of concentration over the difference of distance x. So which actually equals to this. Difference of concentration will be concentration of solution minus bulk concentration. Okay, and this delta is basically the Nernst layer or the distance in mm. All right. So when the concentration of solution is approaching to zero, then this is where your current density will become IL. IL is actually known as limited current density. Okay, is written here, limiting current density, IL. So what happens when you have IL? Okay, IL actually means that your concentration of solution is basically equals to zero. Okay, or most of the ions have been used or it's not there. So what happened is you don't have any active species, no active species, okay, in the electrolyte. So what will happen is your current will be zero. Okay. So IL is actually increased by higher solution concentration, higher temperature, which increases diffusivity, and higher solution agitation, which decrease the flux. Okay. So this is actually what what would be the parameter that can affect the IL. So as I said, IL, you can increase IL or you can increase current by having higher concentration, okay, higher temperature also, which eventually will increase diffusivity. Remember, if you have higher temperature, okay, so what will happen is you will have like more vigorous or more motion, okay, so ions will mobilize, increase, okay, ion motion will increase, and this actually will increase also the diffusivity. All right, so higher solution agitation, this is actually by the effect of convection, also will increase the current density or the limiting current density values. Concentration polarization only becomes important when the current density approach IL. So over here, you can see that this is just part of the curve. You have like potential, okay, versus current density, log I. So this is actually showing you cathodic concentration, okay, cathodic polarization. So of course, when I talk about cathodic polarization, okay, imagine that if you have log I versus current, this is actually the plot that you'll get because it's log, so you'll get a Tefl plot. So half of this is basically anode. Sorry?
Doctor, could you accept Jihad?
Okay, so he just joined.
Yeah.
Okay, all right.
Thank you so much. Sorry to stop you.
It's okay. All right. So half of this curve is basically anode and the other half is actually cathode. So when we actually consider cathode concentration polarization, it means that only half of it, you will get only part of this. It is log I. Log I and also potential. So this is actually being plotted in reverse, potential versus log I. So you notice that over here, the current value is flat. It's not like increasing or what. So this actually indicated that you have a limited current density. So limited current density happens when you have zero concentration of electrolyte. Okay. So another thing that you can see, okay, when you have a flat current density, especially at anodic region, for example, you have here another one, okay, flat at the anodic region. So if you have a limited current density at the anodic region, then what will happen is basically you will experience a so-called passivity, okay? Because in passivity, it means that you already have a stable layer on the surface of your electrode, okay, which in this case will be metal oxide, okay, and this metal oxide doesn't give any changes to your electrode or your metal since it's already been passive, so your metals cannot experience further dissolution or others. Okay. Any questions so far? Anything that you want to ask regarding on concentration, polarization?
Doktor,
Yep.
saya just nak confirm semula. So if we have like a cathodic yang bawah punya graph, so
Okay.
we will have like a limiting current density lah. The flat of the current density
Correct.
ada. Yes. So
Yes.
if we have anodic and then if flat at the anodic current density tu means we have passivity. Betul?
Yes.
Okay.
This one is actually if, as I said, if we have like a flat current density at the anodic, like anodic polarization, this actually will indicate that the metal actually experience passivity.
Okay. Okay, thank you.
Meanwhile, for cathodic, okay, for cathodic region, when you have a limited current density, this can be for many factors. Like for example, if you are working at acidic solution, then meaning that you don't have H plus anymore. H plus or your hydroxide ions is no more. Okay, it's equal to 0. Reason is because maybe most of these have been used during the first linear up, and then after that, all have been used and become stable. Or if we are talking about OH minus, then it means that you have a limited oxygen or probably water. Then it's also creating this flat current density. Okay. All right. So for anodic, as I said, if you have limited current density, this is actually due to passivity, the formation of passive layer. Okay, on your electrode or metal, right? That actually stop the further oxidation process of your metals. Okay, right. Okay, so this is basically to explain what I have explained to you guys even before. When you have a anodic dissolution process, you will have like metal will become ions, and during the concentration polarization for anodic dissolution, it can be ignored because an unlimited supply of metal atom is available at the interface, but at the high corrosion rate, the concentration of Mn plus in the interface is significantly increased and exert a back electromotive force, which results in anodic concentration polarization. Okay, so over here you will see that this is actually the first process that you will see, the active process where most of the metal been dissolved. Okay, but when it reaches saturation, okay, when it reaches saturation, most of the anions have been react and it start to like build I think the so-called the corrosion product or the metal oxides product. So what you can notice is that after that, what will happen is you will experience concentration polarization effect, and after that, the current density, as what I've shown you over here, it's become flat. So this is where the limited current density is, happening for your, cathodic, sorry, anodic oxidation process. Diffusion control of corrosion process, the transport of oxidant to metal surface. So this is basically to explain the cathodic process, the one that I've already explained to you earlier. This is where you have like most of the active process. Okay, like for example over here, oxygen react to produce OH minus, and then after that, after all have been consumed, you will see that it become flat. Okay, so this actually tell you that the corrosion current density is actually equals to the limited current density or limiting current density. moving on to the next one, a resistance over potential. Okay, resistance over potential arises from the pass of electric current through electrolyte solution surrounding the electrode. This IR drop may be offset by closing the tip of lodging capillary to the surface of electrode. It will be significant when the surface outside film forms on the electrode surface as a result of electrochemical reaction. So what does it mean by resistant over potential or over voltage? All right. So this actually in the case of if you have solution, okay, that is not conducting, and also you can experience resistance over potential or over voltage when you have the formation of passive oxide layer on the electrode. Okay, solution that is not conducting. When you have like solution that have a very little conductivity, like for example organic solution or solvent, probably you use organic solvent plus with a salt, okay, just to make it slightly conducting, but maybe the concentration of the salt is not that high, then you can also experience resistance over potential. Another thing is when you have a passive outside layer on the surface of the metals or the electrode, you can also have resistance over potential. Because what does these things actually create as a result? It will actually produce higher resistance. Okay, so higher resistance is basically means that you have lower current. Okay, and when you have a lower current, then the process or the rate of reaction will become lower as well. Okay, so this is actually what does it mean by IR drop. IR drop is basically to tell you that you have current and resistance drop. So this always happen when you have something that jeopardize the electrochemical process, which in this case it will be related to the electrolyte. Okay, electrolyte conductivity or metal surface, metal or electrode surface. Right. So sometimes when you do the measurement, what does this actually happen? Maybe if you're doing polarization process and imagine that you have a grease layer, maybe oil layer on the surface of your metals. Okay. When you do electrochemical measurement, is RE, is WE, this may be your potential stat or what. Okay. So what will happen is that this grease, imagine grease or passive layer, okay, will actually results in IR drop. Oops. Okay. So during the measurement, you will notice that it is not forming a very nice curve. Probably it has some fluctuations, a lot of fluctuations during the measurement. So all these fluctuations is basically with regards to IR drop. Fluctuations during measurement. Okay, this is actually due to the IR drop. So what caused the IR drop is either the electrolyte conductivity or the metal electrode surface. Right. So this actually will create a so-called resistant or potential. Okay. Any questions so far for this one? Anything that you think you are not understand for this part? Is it clear to you guys?
Yes, Doctor.
Okay. So the pathway of electrode reaction, we have seen this
Doctor, I cannot hear you.
Doctor, are you there?
my goodness. Man, I didn't realize that, but like at which slide that I already like disconnect with you guys, because actually my phone is not with me, so I didn't know if you guys have like contacted me or not. Dekat slide yang mana tadi?
Dekat slide pathway of electrode reaction.
Pathway of electrode reaction. Because actually I was explaining, too short of explaining until we almost finished to the mixed potential punya tu. For the mixed potential, did you guys have like saw it? Dekat mana tadi?
No, doktor. Kita orang tak ada.
Tak ada. Oh man. Oh, I have to explain over again. Yang ni tadi dah? Pun tak ada?
Tak ada, doktor.
Man. Jauh dah. Yang ni?
Baru nak start sini.
I see. And then from here, all the way is already like disconnected.
Ya, betul.
Oh. Man, this is serious. Okay. Maksudnya tadi dah lama lah saya disconnect tadi.
Lama jugalah, 10:30.
Dah 10:30? Really?
Yes.
Oh, okay. Very sorry for that. I'm not expecting this to happen. And another thing is, apa tu? My phone is actually not with me. Saya tengah charge tadi. I was charging my phone, so I'm not aware if you guys have like contacted me or what. Okay. So basically, for this one, it's actually telling you guys that when we talk about overpotential, this always in the case that it considers other effect. Okay, like for example, when you have the exchange of current, this is actually due to the activation control, mass transport process, chemical reaction that proceed in the surface layer, and also the surface phenomenon due to the adsorption control, crystallization control, and etc. So this will be some of the parameters that can affect to your overall electrode reaction. So that is why the overall potential values is calculated as the sum of each partial overpotential values. Which over here, you will see that neta is equals to neta activation plus with neta diffusion plus with ohmic resistant overpotential plus with chemical overpotential and plus with crystallization overpotential. And things that you maybe notice is that the words overvoltage. Overvoltage is actually equals to the overpotential values. The rate of the total electrochemical process is determined by overpotential of the slowest partial reaction. Okay. Right. We also have a combined polarization process. Okay. Where in this combined polarization, it means that the anodic and also cathodic process will be considered during the polarization process. Okay. So over there, you have like the total overpotential, which actually equals to neta CT, or it will be depends on what will be the process. But neta CT is actually anodic process, and because it's charge transfer process, okay, and also the cathodic overpotential. So at the lower reaction rates, the charge transfer controls the reaction rate. At the higher reaction rates, the cathodic overpotential controls the reaction rate. So what does it mean by neta? This is actually dissolution overpotential. Dissolution process occurs at anodic site. So that is what I wrote over here. Neta dissolution is actually equals to anodic overpotential. Meanwhile, reduction overpotential is actually equals to cathodic overpotential. Any questions so far? Anything? Ada soalan? Okay. All right. So we move on to the last part. Actually, I like explained this when I was disconnected. I didn't notice that. Very sorry, but I think I've wrote over here. So the last part is basically on mixed potential theory. So what does it mean by mixed potential theory? It means that the overall reaction potential. So the easiest way to explain that is that mixed potential is actually equals to cell potential. Okay, but we consider mixed potential in the case of polarization. Okay, so this is what I wrote over there. Mixed potential theory is actually overall reaction potential which consider polarization process. So based on the following hypothesis, all free corrosion reaction involve at least one anodic and one cathode. It means that during the process, you only have like one anode and also one cathode. During the corrosion, okay, of an electrically isolated metals, the total partial anodic current must be equal to the total partial cathodic current. And for metals, the electrical potential of the metals at the anodic side is equal to that at cathodic side due to the very low resistivity. This may not be valid for semiconductors, particularly if the electrode and if the anode and also cathode side are widely separated. Okay. So actually how to explain mixed potential theory. Imagine that you have iron, okay, dipped in acidic solution and connected to reference electrode. Okay, so you know that during this process, iron will be oxidized to form Fe2+, and then in acid, okay, the cathodic process will be the formation of hydrogen gas. 2H plus 2 electron will form H2. Okay, and each individual ions or species like iron and also hydrogen, it have its own potential value. Okay, like for example, for iron, standard potential value is equals to minus 0.4 volts. Meanwhile, for hydrogen, the standard potential is equal to 0 volts. Then the cell potential is equal as follows. This is actually what you have learned in the first few chapters. Okay, E cell is equals to E cathode minus E anode. 0 minus with minus 0.4, you get 0.4 volt. So this is actually the overall reaction potential. Okay. So the overall reaction potential is actually equals to the mixed potential theory. All right. So as I said, for mixed potential theory, you have to consider one anode and one cathode reaction. So you have like anodic reaction of metal dissolution or metal corrosion. You have the cathodic reaction depending on the electrolyte, whether it's neutral, acidic, okay, or with the addition of oxidizer. Okay, so oxidizer, what does it mean by oxidizer? Okay, oxidizer, it means that the chemical, okay, that can increase the oxidation process. Chemical that is added to the electrolyte, which eventually can increase forward reaction. Okay, more oxygen. In this case, chemicals that have more oxygen. For example, potassium permanganate and also hydrogen peroxide. So when you have potassium permanganate or hydrogen peroxide, or you can also have like what other things, vanadium pentoxide, like is also another chemicals that can that is very rich with oxygen that can increase oxidation process. So when you add oxidizer, what will happen is basically Fe2 plus will become Fe3 plus. Okay, so for mixed potential, you should consider like one half equation for anodic, the other one half equation is coming from cathodic reaction, depending on either it's neutral, acidic, or with the addition of oxidizer. Okay, we took at one examples, okay, over here. I think let me erase it. Sometimes it's quite stressful to know that you're already halfway done and suddenly you notice that you are talking alone. Okay, right. Okay. So basically, as what I have mentioned to you earlier, that for each species, okay, it have its own polarizing anodic and also cathodic curve. Consider that zinc is corroded in acid solution. So you have like zinc, okay, in a container, in a cell, connected with reference electrode in acidic solution. So the active species will be zinc and also H+. Okay, so this will be the anodic reaction and this will be the cathodic reaction. You have the solution of zinc and the formation of hydrogen gas. Okay, right. So the standard potential values for hydrogen is equal to 0. So you'll notice that 0 is over here. And then it have a tendency to oxidize to form this equation and to reduce to form this equation. So that is why for hydrogen polarization, you can have like these two curves. Meanwhile, for zinc, you can have this two curve as well, okay? Because the potential value is somewhere here, minus 0.7. You have like oxidation process that give you half equation and another reduction process to give you another half reaction. Okay, all right. So this graph is actually a TEFL where potential is plotted versus log I. And what does it mean by mixed potential values or mixed potential theory? Okay, so if you notice over here, okay, you'll notice that at this point, if I just extend this linear curve a bit, with this line a bit, we have an intersection of point over here, isn't it? So this is actually the point where we call it as E-core. And this is how you can get the TEFL plot for your zinc with acid reaction. Okay, and this is actually the I-core. All right. So since earlier that I said to you, mixed potential means that you consider both potential, the potential for zinc and the potential for hydrogen, which at the end resulted a so-called or a new potential that we call it as E-core. Okay, so E-core is basically the corrosion potential. Okay, all right. Any questions so far regarding on this? Anything that you want to ask?
So far, okay, Doctor.
This is the same explanation as what I have shown to you guys earlier, where you have like hydrogen and also zinc. Okay. Both actually have the tendency to form its own anodic polarization and cathodic polarization. Similar thing for zinc. Okay. But when we actually consider both species, okay, we have resulted a new potential that is called as mixed potential. And this mixed potential is equals to the E-core. Okay, and this is actually your I-core. You can actually read your I-core values by anti-log the current density values. Then you will get the value. Right. So the same explanation as what I've told you guys earlier. Considering zinc undergoing active corrosion in deaerated hydrochloric acid solution in 25 degrees C. So you know that you have anodic reaction of zinc dissolution. So you notice that the arrow is bigger for forward reaction for the formation of zinc 2 plus. Meanwhile, for the cathodic reaction, the formation of H2 or hydrogen gas, you see that the more intense arrow is pointed at the formation of hydrogen gas. And the Nernst representation for both, for hydrogen reduction reaction is as follows. This is actually the Nernst representation. And for the Nernst representation of zinc oxidation process is this. A mixed electrode is an electrode or metal that is in contact with two or more oxidation reduction systems. Corrosion potential and corrosion current density are determined at the point where the total rate of oxidation and reduction is equal. So you will get equal where the oxidation and reduction process equals. Where it equals means that it intercepts. So when it intercepts, this actually will result you the equal values. I think I will skip this one because this is actually the same explanation as earlier. And another thing that you should notice is that exchange current density during the mixed potential process will depend on electrode composition. Of course, if you have like alloys or what, then the current density value is different. Redox reaction, what would be the oxidation and reduction process? Temperature, okay, temperature of reaction will also give you a different current values. Higher temperature will give you higher current values, surface roughness, okay, and also uniformity of the solution. All right, I think we have talked about oxidizer earlier. So what does it mean by oxidizer? So as I said, by the effect of oxidizer, it means that chemical that is added to the electrolyte. Okay, so what is actually oxidizer? Oxidizer is a chemical that can actually increase oxidation process. Okay, so the driving for corrosion is increased by the addition of a stronger oxidizer, that is a redox system with a half cell electrode potential, much more noble than that of any other present. So consider the corrosion of metal M in acidic containing Fe3+. So in this case, what is mean that when you add oxidizer, okay, the first reaction that you will notice is that the formation of Fe2+. Fe become Fe2+, plus 2 electron. When you add oxidizers such as potassium permanganate, hydrogen peroxide, and whatnot, what will happen is Fe2+ can be converted into Fe3+. So this will be the other reaction. Okay. So the experimental observation that you should notice when you add oxidizer to your electrolyte is that the corrosion potential or E-core will shift it to more positive or more noble direction. Because when you add this chemical, it will increase oxidation process. When you increase the oxidation process, it will actually shift the potential more anodically. Okay. You also notice that the corrosion rate will be increased because when you have like more oxidation process, then the rate will increase as well. And finally, you also notice that the hydrogen evolution rate will be reduced. You see that only little hydrogen will be produced. Why? Because when you have higher rate of forward reaction as compared to reverse reaction, this actually indicate that you have a dominant oxidation process as compared to reduction process. Then that is why the reduction process, which in this case, the hydrogen evolution will be reduced. Okay. So when you add oxidizer, what you should notice in terms of the mixed potential difference. Okay. Of course, you will notice that the total rate of reduction is the sum of the three reduction reactions at any given potential. Okay. Apart from that, the total rate of oxidation is the sum of all three oxidation reactions at any given potential E-core is defined by the intersection of the total oxidation and total reduction line. And in this example, you'll see that the E-core for metal oxidation is the only oxidation, so the total oxidation current density is the corrosion rate. And the total reduction current is the sum of the iron and hydrogen reduction. So what is actually indicates over here? So you will notice that here, okay, if let's say that you didn't add any oxidizer, this is actually the Fe to Fe2 plus curve, and this is actually your hydrogen. This is what your zero potential values. You have like one line over here, another line over here. So if I just like extend this and extend this, you have an overlap somewhere here. So this will be your E-core. If let's say that you didn't put any oxidizer, and this is actually your I-core if you didn't put your oxidizer. But when you add your oxidizer, you will see that the potential values, okay, which is actually addressing the Fe2 plus to Fe2 plus. Another one is Fe2 plus to Fe2 plus. So as mentioned earlier, okay, where will be the E-core value, okay, of this mixed potential? So you just extend the line even further, okay, and then as it mentioned over here, the E-core is defined as the intersection of a total oxidation and reduction line. And then you will also notice that in this example, E-core is the metal oxidation, only oxidation, so that the total oxidation current density is the corrosion rate. Okay. So since we have like additional of oxidizer, so this will be a new line that we consider. Okay. And then the new E-core is basically somewhere here. Okay, so this is actually the new E-core, which is actually where the points you have like the intersection of Fe3 plus with your hydrogen. Okay. So this is where the E-core, the new E-core values, okay, produced with the addition of oxidizer. Is it okay to everyone? Any questions so far?
Doctor,
Yeah.
why is there the dotted line?
Which one?
I mean, it seems like to have a dotted line.
This one.
Yes. Why should we consider this dotted line?
Okay. So this dotted line is actually the total rate of course, this reduction rate. Okay, and this is actually the total of oxidation rate. You will notice that there's slight changes over here, right? Of course, for hydrogen, the reduction line is actually here, can? And then when you add Fe3 plus, earlier on, I told you that when you add oxidizer, what will happen is that your potential will be slightly shifted. So that is why you will notice that this is basically your Fe3 plus line, okay, the reduction line. And then this is where you have the intersection with the hydrogen. So this is where the shifting occurs. So when you have a shifting, okay, just a slightly shift, this actually indicates that it didn't forms over here, but instead it forms to a new point, which is here. Okay, so the dotted line actually means that it is the sum of the over here. I think it's mentioned over here. Is sum of the three reduction reaction. Okay, this is actually the point where you can have the sum of the total reduction process, and also the dotted line over here is the sum of all reduction process, all oxidation process. Okay.
Okay, Doctor.
Any other question? All right, so I think this is also the same thing as what I told you. Okay. So this one actually to tell you where does this dotted line. So if you can see over here, Liana, so this is actually for your hydrogen, kan? Okay, so this is for your Fe3 to Fe2. You have line over here, okay, and this is actually from Fe to Fe2. Okay. So if you notice over here, this the point. I mean, the eco that produced over here is actually the point where you can have all three effects together. Fe2 plus. Okay, this is actually from Fe3 plus. This is actually for your hydrogen reduction. So this is where you have like 3 points all together. So the new eco is basically here. Okay, with the addition of oxidizer. If there is no oxidizer, then your eco should be somewhere here, because this is actually the intersection line. Okay. So of course you will see that there's a shifting of potential. Okay, and why the eco for oxidizer is pointed over here is because at this point you can have a point where these three intersection can occur. Okay, as the sum of the overall reaction. Okay, so the typical polarization plots that you can observe is that either you can get active, I think, process where you have like active oxidation and active reduction. The plot is like this. You can also have the activation control and limited at the cathodic. So you have like active at anode and limited current density at cathode. So why you can have like limited current density at cathode is could be due to the limited oxygen concentration, limited water, or limited acid concentration. You can also have a plot where you have a limited current density at anode and active plot at cathode. So this actually indicates that if you have a limited current density at anode, there's a passivity or passive layer already formed at the electrode surface. And you can also have the combination of both. You can have that both limited current density at anode and cathode, which actually indicates that you have a passive current, formation of passive layer, and also limited current density at cathode due to limited oxygen, limited water, and also acid. Okay. All right. I think later after today, I will, post you a new assignment. It's actually assignment 2, which cover chapter 4. And we are going to look at examples for mixed potential. So in this case, in this example, nickel experienced corrosion in acid solution according to this reaction. So nickel plus with acid will form nickel 2 plus with hydrogen gas. The rate of both oxidation and reduction half reaction are controlled by active polarization. So the first question, compute the rate of oxidation of nickel given the following activation data. Okay, so you are given with the standard potential for nickel and standard potential of hydrogen, anodic current density of nickel and cathodic current density of hydrogen, beta A and also beta C values. B, compute the value of the corrosion potential. And finally, C, rate of corrosion, corrosion rate in MPY, means per year, if the molar mass and density of nickel are 58.69 and 8.908 gram over centimeter cube, respectively. I believe that this example is need to be understood because I think for your assignment and in fact for your test or for your exam, sometimes I do give this kind of question regarding the active polarization. All right. So how to answer that? So this actually the equation that we have seen in the past few slides. Over potential is defined as the difference between the actual potential, okay, of electrode and the equilibrium. So that's why you have this notation. Over potential is equals to applied potential minus with equilibrium potential. Okay. Or if you rearrange, you can get neta A or anodic over potential is equal to applied potential minus with equilibrium potential. And this also the equation that we've seen. This is actually the TEFL equation. Neta A is equal to beta A log IA over I naught. Okay. Neta C is equal to beta C log IC over I naught. A potential that is equals to corrosion potential, you will have this notation. So how you can get this notation is actually by substituting neta A okay, into this equation. So I will get equals to beta A log A or log I naught over, IA over I naught. I can also make it even simpler. Minus beta A log I naught. That is why you get this notation. Okay. So for neta C is like this. You get also this notation, almost similar. It's just that beta C, IC. And when you assume E core is actually equals to E, yeah, then what you will get is you'll get this notation. Equals to log N. Okay. All right. So the common term over here is basically this one. This is actually the common term. Okay. So I just make it simplified. Okay. You will get at the end log I naught is equals to EA anodic potential minus with cathodic potential plus beta A log IA minus beta C log IC over beta A minus beta C. So this formula, okay, I want you to memorize. This is actually how you can get exchange current density. Yeah? I guess in your assignment you have kind of a similar question like this. So you need to calculate, because the question is actually asking what would be the rate of oxidation, because we know that rate is actually equals to current density over NF, isn't it? So we need to calculate what will be current density first. So in order to calculate current density, then you will have to use this formula. Okay. So potential value is actually given. I think I just write the answer over here. You can try after this. Put the values of potential of anodic for nickel and also for hydrogen, beta A and beta C value, okay, anodic current and also cathodic current over beta A and beta C's. See, can you get this value? Okay. And finally, if you anti-log, you will get 8.81 times 10 power of 7. I guess maybe if you have time, just try. I think I didn't put the values over here because it's like a long, I think, derivation or long calculation. You just like put the answer, but you can try, see what you can get or not. So since earlier on, I told you that the rate is actually equals to current density over NF. So once you get the current density, so you just over with the valency, which is equal to 2, multiply with Faraday's constant, 96,500. Then you will get the rate is actually equals to 4.56 times 10 power of negative 12. Okay. All right. So question number 2 or B is actually to calculate the corrosion current, the corrosion potential. Compute the value of corrosion potential. Okay. So since in the derivation we have this notation, okay. So E is actually equal, right? This is actually equal. So you can actually use the current density, the exchange current density that you have obtained from number 1, okay, and then put it in either equation number 1 or either in equation number 2. So in this case, I think we choose to put it here. So E core is actually, if you rearrange from here, just like put here, then it become like EC plus BC minus with BC log I naught. Okay, so you will notice that over here, the E core value is equals to 0.0173. Okay, notice that the beta C is addressed as negative symbol. Okay, exchange current density, yes, and the potential values is equals to 0, because this one actually I put it in for hydrogen. Okay, so that is why it's equal to 0. So you can try after this, okay, whether you can get or not this value. And finally, the last question is actually on the corrosion rate. So this formula we have seen earlier in chapter 3, I guess. Okay, previous chapter. Okay. So the corrosion rate is equals to 0.13 multiplied with I core multiplied with equivalent weight over density. So I core is actually equals to exchange current density I naught. So this should be remembered. Then the value of I core must be in microamperes. So that is why you will notice that it is multiplied with 10 power of 6. So 0.13 multiplied with 8.81 times 10 power of minus 7 times 10 power of 6. Multiply with equivalent weight. Equivalent weight is basically molecular weight over valency. In this case, 58.69 divided by 2. Okay. And the density is actually the density of nickel. Okay. Then you will get the corrosion rate is equals to 0.378 mpy. Okay. Any questions so far? Anything that you would like to ask?
Sir, can you go back to slides 57 or 8?
Which one?
Yeah, this. Doctor, we
Okay.
take the eye corrosion, the same, the point with the 3. That means the shifts eye corrosion also.
You mean for what? For the eco?
The eye corrosion.
Okay, ICO for with addition of oxidizer or not?
Yeah.
With addition of oxidizer, you mean?
Yes. Yeah.
With the okay, with the addition of oxidizer. Since I told you that this is actually the ICO if you didn't put any oxidizer. Okay, but if you add the oxidizer, indicate first where is your eco. The eco will be somewhere here because it actually intersects with one point over here, another point here, and one point here. 3 reactions at one time. Then your eco will be here, because this is actually the new Tafel plot that you will get, and this is actually the ICO. I think, yeah, this is actually mentioned here. This is actually the ICO with the addition of oxidizer.
Okay, Doctor. Thank you so much.
Okay. Any other question? Any other question? Anything? All right, so as I said, I will post your assignment 2 later today. And today also we are going to have quiz. I will post the question also after this in your e-learning. And perhaps by Thursday, okay, we will start a new chapter. Okay, your deadline for assignments, I guess it will be like 1 week. So no need to worry. You can like submit it next week. And if you have any problem regarding on assignment 2, because I think assignment 2 is a bit tough to for you guys. Maybe you really need to understand about the polarization thing, and but if you have like understand it well, then I guess it should be okay for you guys. Okay, so any other things that you want to ask? Anything?
It's clear so far, Doctor.
Okay. All right. So if no other question, then I will adjourn the class. Thank you very much for your kind attention. Once again, I'm very sorry what happened just now. I didn't notice about the disconnection thing. But yeah, hope to see you on Tuesday. With that, have a good day. Thank you very much. And Assalamualaikum warahmatullahi wabarakatuh.
Thank you so much, Doctor. Have a nice day.
You're welcome.
Thank you, Doctor.
Thank you so much, Doctor.
Welcome.